Well, it's good afternoon to you all. We are here live on Yebo Physics. James, and I'll be taking you through the last part on sources of magnetic fields, which will be covering your questions 17 to 25 from TAT number 5, the TAT that you will find available on your on Moodle. So I will not explain much. This is a continuation from what we've been doing in the previous sessions. So we are just gonna continue with what we have in this case, which is an application of Amps law, or measurement of magnetic field intensities at a distance, at a known distance from the source, and in this case from different sources, which in this case would be ideally DC currents flowing through conductors. So for the question that is showing on the screen, I hope you guys can hear me loud and clear. I'm just gonna check with my mics once more. So we should be getting the same feed for both YouTube and Teams, and I'm sure the audio and the video is actually being received well from the other end. So anyway, I'll get on with today's first question, which is question 17. The figure below shows a cross-section of a hollow cylinder, inner radius B, outer radius A, which is a hollow cylindrical conductor that carries a current I parallel to the axis. The current is uniformly distributed over a cross-section of the conductor. What is the magnitude of the magnetic field at the point at a distance R, which is greater than B but less than A, so within that shaded region from the axis of the conductor? Also comment on B, the region that is beyond B, or the region that is within the conductor, which is the empty region to the center or below R equals to A. So first we need to understand where the measurement of this magnetic field is obtained from. So in this case, it is based upon the enclosed current, where we know, according to Amps law, the closed line integral of B dot ds should be equal to mu naught times I. So that means if we have our integral, if the surface, like in this case, the surface shown by the dotted line, encloses a current, so this current is the enclosed current, the current enclosed by that surface about which we are considering our closed path or our closed line integral. So if we do a line integral along the dotted line as shown in this diagram, then which means we have B multiplied by 2 pi r, which is the perimeter of that circle, is equal to mu naught I, and therefore B is equal to mu naught I over 2 pi r. So this is the value of the magnetic field due to the current enclosed, by the region shown by the dotted lines. So now that there is a uniform current density across the shaded region, which is basically giving us the same current per unit area. So that means if we are to use our current density in this case, we definitely know that I enclosed, the enclosed current over the enclosed area, which will be given by pi r squared minus, in this case, B squared, will also be equal to the total current over pi times so this is the difference in area. Pi r squared is the distance from the center to the dotted line. So this is the area enclosed by the total area enclosed by the dotted line, whereas pi b squared is the total area enclosed by the central white part of this diagram. So which means we subtract that, we remain with the shaded region between the white part within the center or the middle of the diagram and the dotted line. So the same applies. Our I will therefore be equal to the current density given in terms of I, the total current, will be I over pi, in this case A squared, which is the external diameter, external radius, minus B squared, which is the internal radius, giving the internal circle that we need to subtract to just get the area of the shaded region. So that means our I enclosed remains as, the pi can cancel out, remains as R squared minus B squared over A squared minus B squared, everything multiplied by I. So I enclosed is a fraction of I given by the part in brackets. So now the magnetic field within that region, the magnetic field that we're evaluating within that region, in this case, like we evaluated it like this, it means this is representing our enclosed current, which we replace by this expression, leading to B equals to mu naught over 2 pi r multiplied by I enclosed, which is R squared minus B squared over A squared minus B squared. So this is the field at the point which is shown by the dotted line, which is a distance r from the center. So multiplied by I. So that's how we have as our solution, which one is that? Mu naught I over 2 pi r, which is that R squared minus B squared over A squared minus B squared. So that will be our answer. Okay. I'm just logged out, so I'll just try to relog. Just bear with me for a moment, please. Okay. So this is chapter 30, sources of magnetic fields. And that's question 17. Okay, so that's our answer for that question. It's mu naught I over 2 pi r multiplied by R squared minus B squared over A squared minus B squared. That's the fraction of the current that's responsible for the magnetic field at that point. That's the enclosed current. So yeah, I won't dwell much on that. The second one, a long hollow cylindrical conductor. So we have a long hollow cylindrical conductor with inner radius 2 millimeters, outer radius 4 millimeters, carries a current of 24 amps distributed uniformly across its cross section. A long wire with a coaxial, which is coaxial with the cylinder, carries an equal current in the opposite direction. What is the magnitude of the magnetic field? 3 millimeters from the axis. So we have the field due to the current enclosed and the field due to the coaxial wire that carries current in the opposite direction. So if I would draw a cross section of this given scenario, we would have something almost similar to this. Okay, then we also have inside it a wire like that, and now the current flows in this wire, 24 amps, a long wire current, an equal current. So the current is the same in both cases. So then we also have current flowing through that region, which is also 24 amps. So that's the region of the hollow cylindrical conductor. So now the magnetic field, with a magnetic field due to the current inside the wire and the current which is inside the hollow cylindrical conductor's surface. So now the inner radius is 2 millimeters. So we know that distance. We can use something else there. So that distance there is 2 millimeters. Then the one to the outer edge is 4 millimeters. And we want to find the magnetic field at 3 millimeters. That's the point where we have to find the magnetic field. So now, because the currents are in opposite directions, it means the magnetic fields at those points will also be opposite. So we have to find the field due to the enclosed current from the conductor and the field due to the line conductor. So we'll call the field in red B1. So the line conductor is responsible at that point for a field B1, and the cylindrical conductor gives us a field B2, and the net field at the point of interest, B net, will be equal to B1 minus B2, because the currents responsible for the two fields are opposite. So if B1 is due to the straight conductor, then this field is supposed to be measured by mu naught I over 2 pi d. I hope my formula is correct. Yes, so d being the distance from the center to the point of measurement. Then the other field due to the conductor will be given by mu naught I over 2 pi d again, multiplied by, in this case, R2 squared minus R1, or let me say RP squared for the point of measurement, minus R1 squared over R2 squared minus R1 squared. So this is like A minus B. We are calling this R1, This is R2. This is RP. Those are, so RP is the same as our D. So we can simply substitute, instead of D there, we use RP to the point of measurement of the field. So now we need to express this mu naught I over 2 pi RP multiplied by 1 minus RP minus R1 squared over R2 squared minus R1 squared. So this is our simple expression. We know that mu naught is 4 pi times 10 to the negative 7. I, we're given I as 24 amps multiplied by 24 over 2 pi. RP is 3 millimeters, which is 3 times 10 to the minus 3. Remember, SI units are important still at this stage. So 1 minus, now we subtract 3 millimeters squared minus R1, which is 2 millimeters squared, or over R2, 4 millimeters squared, minus 2 times 10 to the minus 3 squared. So we can evaluate that. We have our calculator with us here. Let me see how that calculator will look like. So this is 24. I'll make the fraction, the first fraction, 24 times 10 to the power of negative 7 divided by 3, 10 to the 3. 3 times 10 to the power negative 3, I think, to the power of negative 3. Then the other bracket is 1 minus multiplied by 1 minus another fraction, which is 3 10 to the minus 3 squared. Okay, don't trust that. Let me put a proper bracket there and square that, right? Subtracting minus open bracket 2 times 10 to the minus 3 close bracket and square it. Okay. So divided by 4 times 10 to the minus 3 minus 2 times 10 to the minus 3 squared. Did I do this right? I think I don't like this. I don't like this. Ten to the minus 3 and squared there. So this out, and okay. Okay. Okay, I'm only seeing the end of that screen. Let me just copy this again. So we have that first part. Let me just check the last part which I was correcting. This one. Squared. And that one. Squared. So that's 24 for current, 24 amps. So the current is the same, 24 over 310 to the, oh, I divided by 2 there. 2 pi into 4 pi, that should be 2. So I still have that 2 there. I still have that 2 multiplying. Okay. I think this is 2 times 24, 10 to the minus 7 over 3, 10 to the minus 3. Everything multiplied by 1 minus 3, 10 to the minus 3 squared minus 2, 10 to the minus 3 squared all over. So this is all over 4, 10 to the minus 3 squared minus 2, 10 to the minus 3 all squared. So this is 0.93 milli. 0.93 milli, yes. So it gives us 0.93 milli Tesla. So B is that amount. So we do have 0.93. I see that on B. 0.93 millitesla. So that's the two fields adding up. We've got two fields superposing, one due to the hollow cylindrical conductor and the current carried in one direction versus the one from the wire with the current in the opposite direction. Okay, so question number 19. Number 19, we're dealing with a solenoid. So with question 19, a solenoid of 4 centimeters in radius and 4 meters in length has 8,000 uniformly spaced turns and carries a current of 5 amps. So we have something like this. Okay. So with the number of turns there, N is 8,000. Then the length of a solenoid is given by that, L. And this is just 4 meters. And the radius is the distance from the center of the axis of the solenoid, R. And R is 4 centimeters. Then the current carried there, I, is equal to 5 amps. Consider a plane circular surface. So we have a surface, plane circular surface will be something like this. Okay. A plane circular surface located at the center of the solenoid with its axis coincident with the axis of the solenoid. So the axis there is coincident with that of the solenoid. Okay, something like that. Then what that means is its area is perpendicular to the magnetic field inside the solenoid. The question is, what is the magnetic flux through this surface? So to find magnetic flux, phi b, we know that this is flux density multiplied by area. Flux density multiplied by area. So that's BA cos theta, where our theta is 0 because the normal to the area vector of the magnetic field and the area itself are facing the same direction. So the normal, in this case, faces that direction, our normal area vector. So if that's cos 0, that's 1. So it means we just have magnitude of B, magnitude of A. And what is B? B inside the solenoid is given by mu naught N I over L multiplied by the area. So this is the area of the circular plane surface, which is pi times R squared. So 4 pi 10 to the negative 7 multiplied by N, the number of turns, 8,000. The current, 2 amps, no, 5 amps. The length, 4 meters times pi, and the radius squared, 0.02 squared. That's the expression that should give us the flux through this surface. So back to the calculation. We have 4 pi 10 to the negative 7 multiplied by 8,000 multiplied by 5 multiplied by pi multiplied by 0.02 squared and then divided by 4. 1.58 10 to the minus 5. Do we have anything closer to that? So that's 16, roughly that would be 16 micro. So if we take to 2 significant figures, that would be 1.6 10 to the minus 5, which is 16 micro Webers. So the 16 micro should be correct. Okay. So we proceed to question 20. So question 20 deals with a solenoid again, a long solenoid of which is wound with 960 turns per meter of thin wire through which a current of 300 milliamps is maintained. It has a wire carrying 12 amps inserted along the axis of this solenoid. And what is the magnitude of the magnetic field at a 0.2 centimeters from the axis? So the picture again here is that of a solenoid like that with a wire carrying a current along its axis, and the current in the wire is 12 amps, and inside the solenoid we have 360 milliamps. So the magnitude of the magnetic field at a 0.2 centimeters from the axis. So what are the information given there? N, which is the number of turns per unit length, is equal to 960 turns per meter. 960 per meter. Okay. Then the other given information is the diameter is 5 centimeters, so which means the distance from the axis to the solenoid to the wire that makes the solenoid in this case. And that distance there is 2.5 centimeters. And we want to find the magnetic field at a point 2 centimeters from the axis. So that point there is our P, where we have R. So we define R. So the field at point P, which is a radius RP from the axis. So that field, what will it be? The net field, net magnetic field, in this case, B at P is equal to B due to the wire plus B due to the solenoid. So now take note, the B due to the wire, if the current is flowing in the wire from left to right in the direction shown, then the field at point P is out of the plane. So B at point P due to the wire, BW, is out of the plane. So out of the plane will be represented by that. That's for the direction. Then B due to the current in the conductor. If the current is flowing like that, it's flowing in that way, then what that means is if you use the right-hand rule, the field inside the conductor is in the direction of the current. So B due to S is to the right. So we're combining a field that is coming out of the plane to a field that is to the right. So otherwise, we can say this is B in the Z direction. So its direction is the Z, and this one, the direction is the I. The two fields are perpendicular to each other. So when we have a situation like this, it means the magnitude of BP, the magnitude of this field is equals to the root of the magnitude of B due to the wire squared plus B due to the solenoid squared, because they are perpendicular to each other in terms of directions. So now the question is finding BW and BS. The B due to the wire is given by mu naught I over 2 pi d, that's our formula, or 2 pi rp. So that's 4 pi times 10 to the negative 7 multiplied by I inside the wire is 360 milli over 2 pi, and rp is that distance which you said is 2 centimeters, 0.02 meters. So we remove the 2 pi there. We can express our BW as a single value, and that value will be 2 times 10 to the minus 7 multiplied by 360 milli and then divided by, no, not that, and then we divide by 0.02, which is 2 centimeters. We get 3.6 10 to the minus 6. We have 3.6 times 10 to the minus 6. We need to check that, if that's correct. Mu naught I. Okay, sorry, we said this is due to the wire. So if it's due to the wire, this current is not 360, this current is 12. Sorry for that. The correct current there is 12, so we use 12 in this expression, not 360 milli. So we remove that and put a 12 there. 1.2 times 10 to the minus 4, yes. 1.2 times 10 to the negative 4 Tesla. That's the value of BW. And B, due to the solenoid, is mu naught times N times I, where N is the number per unit length. So this is 4 pi times 10 to the negative 7 multiplied by, we said N is 960 per meter, so multiplied by 960, and I is 360 milli. 360 times 10 to the negative 3. So we can evaluate that. 4 pi 10 to the 4 pi times 10 to the power negative 7. Multiply this by 960, the number of turns per unit length, and then multiply by 360 milliamps, which is the 4.34. Is it 360? Where am I getting 360? It's 300. 300. 300 milliamps. 3.62. So that's 3.62 times 10 to the negative 4 Tesla. So we have those two values, and now we combine them according to our equation, which is this one. So the magnitude of the magnetic field at point P is equal to the root of 3.62 times 10 to the negative 4 all squared plus 1.2 times 10 to the minus 4 squared. Okay, so we take the square root, open bracket, 3.62 times 10 to the power negative 4, close bracket, like this, and square, plus, open, 1.2 times 10 to the power negative 4, close bracket, all squared, 3.81. So this is giving us 3.8 10 to the minus 4, which is 0.38 milli. 3.8 times 10 to the negative 4 milli Tesla, which is equivalent to 0.38 milli Tesla. So in terms of the milli Tesla, that's 0.38. That's 0.38, which is what we see here at C. Perfect. Okay, so that's basically one important thing with this question. You have to take note if you are to find the magnitude of these fields. The fields are not just going to add because they are vector fields. So you will need to visualize and identify what direction each field is presenting, and then do the appropriate summation. So for question 21, by using a compass to measure the magnetic field direction at various points adjacent to a long straight wire, you can show that the wire's magnetic field lines are A. Circles that have their centers on the wire and lie in planes perpendicular to the wire. Sounds correct. Straight lines in space? No. The compass will trace a magnetic field which is a circular path. So it should be circles. Straight lines is already out. Circles that have a wire lying along a diameter of the circle. So the magnetic field do not have the wire as the diameter. Straight lines in space, so it's basically A. So these are circles that have their centers on the wire and lie in planes perpendicular to the wire. So if we have a wire with a current, then this magnetic field will be given by circles which are difficult to draw, but will be something like that. So those are the circles that show the B field for a current I. So right hand row. Okay, got it. So the next part, that was quite easy. A solenoid consists of 100 circular turns of copper wire. Parts of 3 turns ABC are shown below. When a current flows through the coil, so if the current is going in circles like that, that will be kind of we can call that a clockwise direction from looking from the right side of the diagram. But besides, when we have a flow like that, what then happens? Both A and C are repelled by B. So this is about the forces. Like currents attract. So we know that like currents attract. Unlike currents repel. So this is opposite to what we know with charges or with magnetic poles. North and south should attract, whereas positive and negative should also attract in electric fields. But when you deal with flowing currents, the currents that are in the same direction will result in a force of one conductor towards the other. So like currents will attract, and like currents will repel. So that's one thing for sure. So that means both A and C are repelled by B. There's no repulsion. Both A and C are attracted by B, yes. So anything that talks of repulsion is out. Excuse me. So in this case, our solution or our best answer should be C. The best answer should be C. Then question 23, we're almost getting to the end. So you should have picked something so far. Anyway, a toroid is made of 2000 turns. So we talk of a toroid. How do I draw a toroid? So it will be No. Let me draw the donut shape first. Then I can now put my wire. Okay, so that's more of a toroid. So it has 2000 turns of wire and the radius is 2 centimeters. So the radius, that's 2 centimeters, is basically this distance from the center to R. So R equals to 2 centimeters from the center to the edge. Then it is made of 2000 turns of wire of radius 2 centimeters formed into a donut shape. So that's the donut shape now, which goes around like this with an inner radius. So the inner radius there of the donut shape is 10. And the outer radius is 14. So this is the outer radius. That's gonna be 14 centimeters. So the difference between 14 and 10 is 4, and 4 is basically the diameter of the tens, so that the radius is 2. So that's quite clear. Now, when a current of 30 amps, so we have a current which is 30 amps that goes in there and comes out through the other end. Is the current in the toroid, the magnetic field at a distance of 11 centimeters from the center of the toroid is, so 11 centimeters, we are just a centimeter into the conductor around this donut shape. So R at 11, B at R equals to 11 is equal to, the formula for the magnetic field inside the toroid is mu naught N I over 2, is it over 2 pi? No, over T, over R. Should be mu naught Ni over R. Let me cross check. For a toroid, is it over R or over 2 pi R? Mu naught Ni over 2 pi R, over 2 pi R. Okay. Okay, so that's the formula that we're gonna use. So with this formula, what follows? We know that our R is 11 centimeters. So we have B at R equals to 11 equals to 4 pi times 10 to the negative 7 multiplied by the number of tens. In this case, this toroid is a 2010 toroid with 2010s and the current being 30 amps. Let's see if that gives us anything close to the answers. 4 pi times 10 to the power negative 7 multiplied by 60,000 and then divided by open bracket 2 pi times 11 times 10 to the power negative 2. So this is giving 0.109 Tesla. B at that point is 0.109 Tesla. And that's correct. So the identification of the correct formula there is also quite important. Then question number 24. Consider two copper solenoids, 1 and 2 respectively, each made of 2000 tens per meter. So the 10 or number density of tens there is the same. But solenoid 1 is 2 meters long, while solenoid 2 is 1 meter long. When equal currents are present in the two solenoids, the ratio of the magnetic field B1 along the axis of the solenoid 1 to the magnetic field B2 along the axis of the solenoid 2, which is B1 over B2 is. So remember, for a solenoid, we said B equals to mu naught, the number density I, started proportional to mu naught, if ever we are to mu itself, if ever we are to change from free space to some magnetic material, then it will increase the field. The number of turns per unit length is also second factor, and the current. So it's directly proportional to those factors, and it is independent of, at the end of the day, it becomes independent of the length itself. So because this n is the number per unit length. So if you keep the number per unit length constant, then which means your B should be the same. If I is constant, mu is the same, which is free space permeability, and the number per unit length is the same. So it would mean for a greater number of turns, we have a greater length and still maintain the same B. So in this case, since the length of one is twice the other, it means the number of turns in that one, which is longer, is also twice. So that keeps this ratio constant. So we have the same number per unit length. So if the length is twice, the number is also twice. And that gives us the same magnetic field, such that B1 over B2 is a ratio equal to 1. So we can write in our working B1 is mu naught N times I1, and B2 is mu naught, N is the same, so each is made with 2000 tens per meter times I2, such that with equal currents, B1 over B2 equals to mu naught Ni over mu naught Ni, because I1 equals to I2. So everything reduces to simply 1 unit. So it's a unit ratio. Okay, then on average in a ferromagnetic domain, permanent atomic magnetic moments are aligned. So for a ferromagnetic material that has magnetism within it, we have the domains aligned parallel to each other, which is what enhances the magnetizability of that material. So that's all for this chapter on magnetic sources. I hope you guys would benefit from it as you go through it. If ever you'd have any questions whatsoever, any other time when we are live, you are welcome to join us, and we'll be ready and willing to assist you for your benefit. Otherwise, from me and everyone at Yebo Physics, it's bye-bye for now. All the best with your studies.